This is a question I love to death, so you can expect to see something like this on your exam. It covers a ton of different chapters. An unknown gas is a mass of that. This gas was contained in a 1 liter flask at a pressure of that and a temperature of 50 or 323. What is the molar mass of the gas? All right, so we go and we look at the problem we did a while ago, and I already did this problem, but it's where we solve for density. Density was equal to, I don't remember. Density would be PM over RT, it looks like, if I rewrote that. But in that equation, which was just a variation of the ideal gas law, we could rewrite that for the mass. The molar mass is equal to dRT over the pressure. So I already did all this. The density is sort of hidden here. It doesn't say the density of something, but it gives you 2.66 grams in a certain volume. So that's your density, grams per liter. So I just put a 1. Mathematically, that's pointless, but that was just to show you that this is the density, 2.66 grams per liter. All right, R is 0.0821, because it always is. The temperature is in Kelvin, and the P is in ATM. When I plug that all in, I got 71.69. All right, so now that is just part A. Part B, if we go back, it says if the gas is 85.6% carbon and 14.3% H, what is the molecular formula? So that takes us, and I've already done this, it takes us way back to chapter 3. So in part B, you may recall how we did this. We first just said, all right, I have 100 grams of this. If I had 100 grams of this CH, I'd have 85.6 grams of carbon and 14.3 grams of hydrogen. This is from chapter 3, so if you get lost, you can review there. So then you convert them to moles by dividing by their molar mass. So this is moles of C, this is moles of H. And then once we had these two numbers, we would divide both of them by the smaller of the two answers to find my ratio. When I did that math, I got a 1, obviously, but then this one was a 2.4. And we usually want this to equal a whole number, but 2.4 is not a whole number. And there's some rounding, so all this will be a tiny bit off, but it's good enough. All right, in order to make a 0.4 become a whole number, we multiply it by 5, because 4 times 5 is 20, or it ends with a 0. So what I do is I take both of these answers here, and I multiply them by 5. 1 times 5 was 5, 2.4 times 5 was 12. All right, once I have that, I have the formula of this hydrocarbon is C5H12. Then I would compare that to part A. In part A, we found it to be 71.69. 71.69 is pretty much the same thing as 72, especially since we rounded a ton. Now, if these are not the same number, they're usually a multiple, and then you just have to double or triple or do whatever you need to make them match each other. All right, so far that's part B. All right, so that's chapter 10 and chapter 3. So that's a C. I have no idea where that came from. All right, and we'll move to part C. Oh, that's where it came from. Part C says to draw the structure and indicate the hybridization. So this will be chapters 8 and 9, which we just finished. So I can come through here, and I already drew it out. It's a very simple one, since it was C5H12. Since 12 is 2x plus 2, or 2 times 5 plus 2. That meant all of these were single bonds. It says to find it of just the central carbon atom, so that's the one I drew in red. All right, since it is got 4 electron domains, 1, 2, 3, 4, that means it's tetrahedral. Its hybridization must be sp3. So far, hopefully, this is going pretty well. Let's come back to D. If the gas were reacted with oxygen, what type of reaction would this be? That's a combustion reaction. I don't know if you can hear my kids laughing upstairs, but if so, one of them has the funniest laugh ever. All right, combustion. Pause and yell, because I'm a good dad like that. Give the balanced reaction, so it's just C5, H12, oh, that's ugly, plus O2 goes to CO2 plus H2O. And it's a combustion, so I'm going to follow those tricks. I'm going to put a 2 here. 2 times 5 is 10. This is a 12, even though it's ugly. I'm going to put a 12 here. Then I have 2 times 10 is 20, plus 12 more. That's 32. I divide that in half and I get 16. Now, since these are all even for this part of the problem, you definitely want to divide these. So I'm going to say 1, 8, 5, 6 would be the best part for E. Okay, so that goes back to 3 and 4. So we're doing awesome. So I went ahead and paused it and worked through letter F. Took me a good solid 5-6 minutes, and it's down here below. So you'll remember, save this in case something goes wrong. This is just from chapter 8, which we just finished up. We use this table to determine the heat of combustion, and if you remember, that's the broken minus formed from this table. So I went ahead and did all of it. I'll just talk through it pretty quick. So the first thing is I drew it out and I counted up the number of bonds broken or formed on each side, and that's this first row here. All right, now I brought the coefficients down. That's where the 1 came from. That's where the 8 came from. Here's where the 5 came from. Here's where the 6 came from. All right, and then this 4 came from here. 1, 2, 3, 4 carbon to carbon bonds, and that will end up being 348 down here. The 12 came from all the rest of the hydrogens attached, and then I put C to H, and that's the 413 that you can see down here. So I carried the coefficient, and then these are the number of times the bonds were broken in each one. All right, the number of times the bond between O and O was broken was 1. But then 8 is the coefficient. Then here, this happens twice, so that's where this 2 came from, and the 5 was the coefficient. I found these numbers from the table. All right, coming up here, O and H break twice, or they're formed technically, but the math's the same. They break twice, that's where this 2 comes from, and the 6 comes from the coefficient. Alright, so then I did this a little different than normal just to try and make sure it was super stepwise. I did each piece and found the total for each piece. Alright, and then I did the math underneath. So I took the coefficient times the number of times the bonds times the energy. I summed it up on the left. I summed it up for each thing on the right. And I ended up with these individual values. So the C5H12, when it all breaks apart, it's 6348. When 8 oxygens break up, you get 3960. All right, when 5 carbon dioxides are formed, you get 7990. When 6 water are formed, you get 5556. All right, then I added these together on both sides, but then I subtract the broken minus the formed. So 10308, that's when these two are added together. The 13546 is when those two are added together. You subtract and you get the total change in energy is equal to negative 3238 kilojoules. Hopefully I did that all right and typed the math into my calculator right. And I don't know why I did that. And that should be that problem. Hopefully that was successful. I know that takes a lot of time, so does problem number 4. But hopefully when you come back from the break, you'll be ready to roll on any type of problem that we will do.